Hello, in this video we're going to go over a sample exam on surface and line integrals. The first problem is asking us to show that this vector field is conservative without finding a potential function. So in order to show a vector field is conservative, we need to show two things. First, curl of that vector field is 0, and second, the vector field is defined everywhere. So if you evaluate the curl of this f, we are going to get I, so we'll have to find the cross product of partials and the vector field. So this is yz, xz, yx minus 1. So this is going to be eliminating the first column. We get derivative of this one with respect to y, that is x, minus derivative of this one with respect to z, which is also x. I minus eliminating the second column and taking the derivative of this one with respect to x, we get y, and taking the derivative of this one with respect to z, we also get y. And eliminating the last column, we get z minus zk. And of course, this is 0. And also note that this vector field is defined on the entire three-dimensional space. So f is defined on the entire 3D space, and that's why f is conservative. So the next thing we're going to do is we're going to find a potential function and find the line integral, because they asked us to find the line integral of this f over the given curve. Okay, so we will go ahead and evaluate a potential function. So we'll find a potential function. So gradient of f is equal to vector field. Okay, so what does that mean? It means f sub x is equal to yz. So we'll take that and integrate that with respect to x. So we get f is xyz plus a function of y and z. The second partial with respect to y, that would have to be the second component, which is xz, and f sub z would have to be yx minus 1. So we'll take the first one. I'm going to number these equations. We'll take the first one, what we got, and plug it into the second equation. Partial of that with respect to y is xz plus g sub y. That would have to be xz. So that tells us that g sub y is 0. So that means g is equal to a function of z only. So that tells us f is going to be xyz plus h of z. We'll take that and plug it into the third equation. Partial of that with respect to z is going to be xy plus h prime of z. That is going to be yx minus 1. So that means h prime of z is equal to negative 1, which means we have h of z equals negative z. Now this is not the only answer to this, but this is one of them that works. And we only need one potential function. So f would be xyz minus z. So this is a potential function. So now that we found one potential function, we can evaluate the line integral by evaluating this at the endpoint. So f dot dr is going to be f of the endpoint, the terminal point, which is 0, 1, 3, minus f of the initial point, which is 1, negative 1, 2. Okay, so f of 0, 1, 3, we'll have to plug in 0 times 1 times 3, that's 0, minus z, minus, product of all three of them is negative 2, minus z. So that would be negative 3 plus 4, so the answer is in fact 1. Okay, let's look at the next problem. Assume a wire is positioned at the curve of intersection of the cylinder and the plane. Suppose the mass density is given by delta of xyz equals root 1 minus xy. Okay, so r equals 1 is going to be a cylinder with z as its axis. So z-axis is the axis of the cylinder. And then we have a plane. It's like a tilted plane. So the intersection, and we know that like this point 1, 0, 0, which is a point on that cylinder, is on that plane, and so is this point 0, 1, 0 is also on that plane. So the intersection would be a curve. It's like an ellipse, and of course we get something like this as the intersection. Okay, so we get an ellipse like this as the intersection. This is our curve C, and we don't need an orientation because we are evaluating a line integral of a scalar function. So that's why we don't need an orientation for this curve. So we want to find the total mass of this wire. So what is the total mass? Well, the total mass is line integral of density, which is root 1 minus xy ds. So this is the line integral that evaluates the total mass. So it's the line integral of density with respect to arc length. So first, we need a parameterization for this curve. So how do we parameterize the curve? Well, it is inside on a cylinder. So one of the parameters would be theta, and because it's a curve, you only need one parameter. So if you look at the curve, it's on the cylinder. So the x coordinate would be cosine, y coordinate would be sine of theta, and z coordinate is evaluated from this one. So z is going to be 1 minus x minus y. So this is our xyz. Next, we're going to have to find ds. ds is magnitude of derivative. So let's take the derivative of this r. So derivative is going to be minus sine of theta, cosine of theta. Derivative of 1 is 0. Derivative of cosine is negative sine. So that's plus sine minus cosine. We'll take the magnitude of this one. So magnitude of r prime theta is going to be square root of sine squared theta plus cosine squared theta plus sine minus cosine squared. So this is going to be square root of 1 sine squared plus cosine squared is 1 plus sine squared plus cosine squared minus 2 sine theta cosine theta. And again, we have another 1 right there. So we get 2 minus 2 sine theta cosine of theta. So that's a magnitude of r prime. So now the line integral of root 1 minus xy ds is going to be integral. So the parameterization was cosine sine 1 minus cosine sine, and limits of theta are from 0 to 2 pi because it's a full circle centered at the origin. So we get 0 to 2 pi root 1 minus, well, the integrand would have to be written in terms of r of theta, cosine of theta times sine of theta times ds, which is root 2 minus 2 sine theta cosine theta d theta. Now if we factor root 2, we get 0 to 2 pi root 2, and we are going to get 1 minus cosine of theta sine of theta d theta. Now, this is relatively easy to integrate. If we take out the root 2, integral of 1 is going to be theta. Integral of cosine sine is going to be sine squared theta divided by 2. Because when you take the derivative of sine squared, you get 2 sine theta cosine of theta. So you have to divide by 2. And that has to be evaluated from 0 to 2 pi. When we plug in 0, everything is 0. When we plug in 2 pi, the only thing that is non-zero is the first theta. So this is 2 root 2 pi as the final answer. Suppose C is the triangle whose vertices are 1, 0, 0. So again, even if they hadn't asked us to sketch the graph, we will have to sketch it. So we will sketch the curve. It's a triangle. They told us it's a triangle. Vertices are 1, 0, 0, 0, 1, 0, and 0, 0, 1. So these are the vertices. And they also said the orientation is clockwise when viewed from above. So we are looking at this from above. The orientation is clockwise. So it would have to be this way. And they're asking us to indicate the orientation and sketch the graph. So we did those two. Use Stokes theorem to evaluate this line integral. And they also gave us a hint that the plane is going to be, and the equation of the plane is x plus y plus z equals 1. So in order to use the Stokes theorem, we need a surface whose boundary is C. So what surface? Clearly the plane, the portion of the plane that is inside the triangle is a good choice of the surface. So let sigma be the interior of the triangle. Okay, so that's what sigma is. And then we need the orientation. So by the right hand rule, this would have to be oriented downward. Next, we're going to find the curl of our vector field. So our vector field is given as, let's look at the vector field. They gave us as x plus y I and zj and plus 2yk. This is our vector field. Okay, so this is our vector field. So next we're going to have to find the curl of this one. So some of these can be done in different orders. So we'll have to find the curl at some point. Now it doesn't have to be the very first step, it could be also later. Partial with respect to x, partial with respect to y, partial with respect to z, x plus y, z 2y, that's equal to. So eliminate the first column, we get 1 minus 1 I. Eliminate the second column, we get 0 minus 0j. And eliminate the last column, we get 0 minus 1k. So this is nice. So this is only negative k. So the first two components are just 0. So we can keep this in mind when we are finding the normal vector. Okay, so that's the first thing. We found the curl. Now we have to parameterize sigma. So sigma is given as r of xy. Because this is given as x plus y plus z equals 1, we could just write it down as x comma y comma 1 minus x minus y. And then the limits of x and y are the projection onto the xy plane. So this is the parameter region for x and y. So the bottom is the parameter region for x and y. And xy are in R. And what is R? R is this triangle with a right triangle with bases on the two axes, x and y axis of length 1. So that is our r of xy. Next, we have to find rx cross ry. We had a formula for that. It was negative fx. So this is our f. So negative derivative of this one with respect to x, which is negative 1, negative fy, and 1. Now we'll have to find we have to make sure that the orientation matches. The orientation, it was supposed to be downward. So this is upward. So we'll have to consider negative of that. So we will use negative 1, negative 1, negative 1. Okay, so we found this one as well. Now we can set up the line integral and relate it to the surface integral. So this is what we're going to use. This is where we're going to use the Stokes theorem. So by the Stokes theorem, we are going to get the surface integral, and line integrals are the same. So this would be curl of f dot n ds. Okay, so let's just do the substitutions. So curl of f we evaluated as negative k. N we evaluated as negative 1, negative 1, negative 1 dA. Now, if you find the dot product of these two, that's the double integral over 1 of 1 dA. So now what is this? This is the area of r, which is just 1/2 because the base is 1, height is also 1. And let's make sure we followed the instructions, and yes, so they said evaluate that. So we finally evaluated the line integral. Okay, so next, let sigma be the part of the paraboloid xz equals 1 minus x squared minus y squared above the xy plane. So let me draw a diagram as usual. Even if they hadn't asked me, I would draw it. So it is this paraboloid. Sigma is part of the paraboloid above the xy plane along with the disk in the xy plane. And the orientation is outward. So this is outward, this is basically downward. So this part is upward and this part is downward. So this is sigma. We want to evaluate this surface integral over this sigma. Because it's a closed surface, we can evaluate that using divergence theorem. So let E be the region bounded by sigma. So we're going to apply the divergence theorem. So by the divergence theorem, the given surface integral equals, so first I'll have to make sure that the orientation matches the orientation in the divergence theorem, and it does. It was outward and this is also outward. So it will have to be this triple integral surface integral over E of the divergence. So derivative of this one with respect to x, that's 0, plus derivative of this one with respect to y, that's 2y, plus derivative of the last one with respect to z, which is 1, dv. So this is what we get. So we get derivative of the first one with respect to x, which is 0, the second one with respect to y, and the third one with respect to z. Now we'll have to evaluate this surface integral, or triple integral rather. This is no longer a surface integral, it's a triple integral. Let's see what the instruction says. Name the theorem that you use. Stop when you get an iterated integral in cylindrical coordinates. Okay, so we're going to use cylindrical coordinates. So the top of this region, the top is z equals 1 minus x squared minus y squared, which is 1 minus r squared. And the bottom is z equals 0. So when we use cylindrical coordinates, y is r sine theta, dv is r dz dr d theta. Z goes from the bottom of 0 to the top of 1 minus r squared. R goes from 0 to 1 because on the xy plane, the projection on the xy plane is of radius 1 because the bottom is a disk, x squared plus y squared less than or equal to 1. So 0 to 1, and theta goes from 0 to 2 pi. And they did not ask us to evaluate. In fact, they explicitly asked us to not evaluate. Stop when you get an iterated integral in cylindrical coordinates. So I will see you in the next video.